afternoon to all of you, faculty, colleagues, students, and other members from other universities and institutions. I welcome all of you on behalf of the Department of Chemistry to the webinar specially arranged for the benefit of all research scholars and faculty to know about each other at a time when we are confined largely to stay at home and do our research. It is a great pleasure for me to have with me Professor P. Ramamurthy, FNASE, is the Fellow of the National Academy of Sciences, to give the lecture today, the webinar today. Professor Ramamurthy is currently, of course, he was former head of the department and a professor in the Department of Inorganic Chemistry, University of Madras. And many of you, I'm sure, know about the National Center for Ultrafast Processes, which was started many years ago with him at the helm of the younger faculty at that time, along with Professor Rajan, who was the head of the center. And the center has been built, and all the activities which are going on can be credited largely to the efforts of Professor Ramamurthy. On my behalf, as well as on the department's behalf, I am thankful to Professor Ramamurthy for agreeing to give the seminar today. A brief profile of him is what I would like to tell all the listeners. He did his undergraduate chemistry in Chennai, in the University of Madras, in A.M. Jain College, and later did his master's in Loyola College, the University of Madras again. Did his PhD in the Department of Inorganic Chemistry under the supervision of the late Professor P. Natarajan, with whom, of course, he shared not only offices but also the centers and many other committees. Later, he did his postdoctoral research in the University of Haute Alsace in Mulhouse, France. He has many academic contributions and many awards. And he started as a lecturer in the Department of Inorganic Chemistry in 1987 in the field of ultrafast spectroscopy and photosciences. And this led to the later establishment of the National Center for Ultrafast Processes, state-of-the-art lasers and facilities. And also he was interested in the excited state electron transfer and photochemistry of new family of laser dyes, NADH model compounds. And also in the area of the solvation dynamics of intramolecular charge transfer state in homogeneous and micro heterogeneous environments, and photonic nanomaterials, including carbon dots. He has many research publications, more than 120 of them, and obviously in all high impact journals, and has been awarded the University Grants Commission's Career Award in 1993, and the CRSI, what we call a CRSI Bronze Medal, is the Chemical Research Society of India, which has been now very popular and is pushing chemistry across all the frontiers with both faculty and students. He also was elected later as a Fellow of the National Academy of Sciences, and in 2004 he has been awarded the Tamil Nadu Scientist Award, known as TANSA, and has delivered many invited talks. In terms of his research projects, he has completed a dozen projects, both as a DST Young Scientist and DST IRFA, CSIR, UGC, DAE, ISRO, and other DST SERC agencies, and has mobilized a large amount of money, close to 7 crores, to the University of Madras, which is a very large amount, considering that he works in a very traditional established university, which is more than 150, 170 years old now. The research grants have facilitated him to set up this facility. And to this date, he has produced 21 PhD students. And his MSc teaching program is initiated in the area of photonics and the biophotonics with the financial support from the Grants Commission. It's a great pleasure, Professor Ramamurthy, to have you here, and we look forward to listening to your lecture and also the interactions that we will have subsequently with all the participants. Over to you, Professor Ramamurthy, now.
Thank you, Mangal Sundar, for the nice words of introduction. In fact, I am thankful to the Department of Chemistry, IITMadras, and this has given me an opportunity to share the work that we have done at the University of Madras Ultrafast Center.
Yeah, I missed one thing. in the introduction.
Yeah.
You are now part of us.
Yeah, of course.
You are now part of us as the adjunct faculty. I should have said that in the beginning, but I think that's the last thing we should say, because all the achievements that you have done so far are all outside the Department of Chemistry and IIT Madras.
Of course,
We are very happy to own you now as part of us.
Thank you.
Please go ahead.
So this has given me an opportunity to share the findings that we have done at the University of Madras, and we will discuss about the last part of the work that we have done before my retirement, that is the carbon dots, and we'll look at the photophysical behavior and excited state reactions of all these materials. And I think I'll go with the PowerPoint projection right away. So the talk that I really going to give today is the carbon dots, which are really making the new materials with a lot of fluorescence sensing properties, imaging applications, and donor acceptor property. These are the material that we have been synthesizing it from different sources, and I thought it will be apt to discuss about the behavior of this material and findings of on this material from our laboratory. Now, before I start, I would like to acknowledge, because generally we forget the people, those who have contributed for the work. And the 5 of my students, basically 3 of them are PhD students, V. Ramanan, Kaviyarasan, and Sendil. And they're all the PhD students. And other 2 students, the Amrita Surya and Supriya, are the summer students from Indian Academy of Sciences. Really, the funding also came from Department of Science and Technology, CSIR, and Indian Academy of Sciences towards the fellowship of last 2 students. And I'm really grateful, and I should acknowledge this. Right, the outline of my talk I've organized such a way that I'll give some basis, because there are some different mixed audience, and I'll give some basic introduction to the subject of carbon dots. And the first part of our contribution and finding is from the carbon dots from the algal blooms. I will start with it as the first part. The second part is the jackfruit seeds. This is really converted to carbon dots, and it is also nitrogen doped. And what are the behavior, photophysical properties we will explore. And the waste material also we have used it was a polystyrene material, and we have really used it to convert into carbon dots and see how it can be utilized for the sensing of materials. And multifunctional carbon dots from the basic organic molecule like itaconic acid and glycine were synthesized, and the itaconic acid finds a lot of application towards the metal sensing like iron 3+, and bifunctional carbon dots from the glycine. We have modified the already reported synthesis, which we made it like a dialysis free. When you synthesize all these carbon dots, the purification is a major issue. So we made a synthesis such a way that the purification of this can be avoided. We still got the good material, and the application of that goes towards the photoredox property. This is how I have organized my presentation, such a way that it really gives you the whole details or the different types of the carbon materials. Now, to briefly introduce about the carbon material, carbon allotropes, if you look at it, you have a 0-dimensional carbon dots like a fullerenes, and onion-like carbon, and carbon dots, nanodiamond, and three-dimensional, one-dimensional is your carbon nanohorns, and your carbon nanotubes or multi-wall carbon nanotubes. You can also look at the 2-dimensional sheet-like a material, graphene, and multi-layered graphitic materials, and so on. This is how you have the variety of carbon allotropes available, which are historic and all that many of us studied from the textbooks itself. Now, how do we really make the new materials out of that is the new learning. Now, one can make a nano diamond from the diamond by making a nano cutting. You can look at the graphene sheet. Graphite sheet can be obtained from your graphite, and make a small folding that can give you the carbon nanotube, and cut into small pieces, and that gives you the carbon quantum dots. You can also oxidize this to get your graphene oxide, and make into small component, cut it, and that gives you graphene oxide quantum dot. This is the whole story about the preparing smaller dimension material from the graphene, and then graphite or carbon derivatives, and so on. Now, what is the importance of the carbon dot? This is a general issue. We have to look at it, and why we were interested in looking at the carbon dots. If you look at the carbon dot itself is basically an accidental discovery during the purification of the single wall carbon nanotubes by Zhu et al. In 2004. Carbon dots are small carbon nanoparticle less than 10 nanometer in size, and with some form of the surface passivation one can have it. Series tend to have a huge impact in both the health and the environmental application because of their potential to serve as a non-toxic replacement for the traditional heavy metal based quantum dots. So these are the important aspects one normally looks at it in imaging and so on. And photoluminescent carbon dots are becoming promising and alternative to the metal-based semiconductor quantum dots because of their biocompatibility, physicochemical, optical, and electronic properties. This is where many people are interested in the synthesis of new materials, different functionalization on the surface of the carbon dots. Now, what are really, there are different types of carbon dots one can talk about it. Carbon dots called the graphene quantum dots, and you can have the carbon nanodots, or you can have the surface modification by polymers, so you call them as a polymer encapsulated quantum dots. These are the different family or types of the carbon dots one can look at it. Now, you always have a question, what is the structure of the carbon dot? Basically, if you look at the carbon, what it is made up of, it is not like a metal nanoparticle, and so it's basically a small organic molecule and really put together. So you can look at the carbon dots are composed of graphene and graphene oxide sheet fused together, diamond-like insertion and containing amorphous and structural elements. Now, based on the literature available, you can see that the carbon dot can be viewed as a highly defected composition of the coexisting of aromatic and aliphatic regions. So we have the graphitic and the diamond-like structure. This is how the basic definition that one can say for the carbon dot structure. Now, why you have the interest, what kind of an application one can derive out of these carbon dots is a fluorescent carbon dots are fascinating luminescent material. This is how we say that it has a lot of features, as well as it's also promising building blocks for the future nano devices. And you can really look at the photophysical properties, and they are interesting and exciting also to understand the dimension of the nano sizes. And these tend to have a huge impact on both on the health and environmental application because of their potential to serve as a non-toxic replacement to the traditional heavy metal based quantum dots. Now, if you look at the different areas of application, one can think of the application in the area of biomedicine, optronics, sensors, and catalysis. These are the areas one can take this material and apply it and find a lot of application for these materials. Now, if you look at the synthesis of general nano dimension material, we always say that the top-down approach, the other one is the bottom-up approach. And top-down is, of course, this is for the benefit of students. So you have a larger size material to a smaller dimension. This is possible by using a laser ablation, electrochemical arc discharger. These are possible to have the top-down approach. You can also have the bottom-up approach from the smaller organic molecule, and then you can use your ultrasonic, hydrothermal, and microwave pyrolysis to have the carbon dot. These are the basic methodologies one follows it to synthesize your carbon new family of carbon dots. You can have a lot of modification on the surfaces. You can have a doping on this carbon dot. These are all the facilities. As you modify the surface, as you really dope the material, so you can have a different properties and exciting properties are coming up. Now, to begin with the first component, first part of my presentation, the first one is from the algal. In fact, this was during the rainy season, we found a lot of algae formation into our Taramani campus. So we thought, why don't we convert this into a carbon dot? That's how we started basically. And we could really see that the nice quantum dots are coming up, and these are very highly biocompatible. And we'll look at the details. I've given you kind of a table TOC picture here, and you can look at this. This is basically the bottom-up approach of synthesis of this, and you can have the highly luminescent carbon dots really coming up this from plant biomass, and this approach is completely green, and also it is a faster one to prepare it. And the series prepared were highly functionalized and also photostable, biocompatible. So series have demonstrated as a very good biomarker for the bioimaging. Now, when you synthesize all this material, optimization of the parameters like your input material. So if we have taken the phosphoric acid as a material, we have optimized the concentration of the phosphoric acid, varying the percentages, one can see it. Now, our reference is what is the quantum efficiency? When do we get the highest quantum efficiency? That is the condition, we call it like an optimum condition for the synthesis of the carbon quantum dots. So we could see that, at the 40% of the phosphoric acid, we get a very good quantum efficiency of almost 13%. And we adopted the method of microwave power is something like a 600 watt, 5 minutes of all this reaction condition, and weight of the algae was kept constant. Quantum efficiency is better at the 40%. You can see that from the data. Now this is how one can standardize the procedure of synthesis of your carbon dot, so varying the parameters and standardizing them when you have the multiple parameter variation. Now reaction condition, again, we also tune the microwave power and time of the microwave irradiation. We found that the 600 watt was an optimal, and the time were around 6 minutes to 7 minutes. We could get a good quantity of the carbon dots also. So this is the important aspect. When you look at the synthesis using the microwave, you maintain the power and the time of irradiation and the reagents ratio that we take up. Now, basic synthesis that is involved in this is using a microwave power with a 60 watt for 6 minutes. In a normal domestic microwave oven itself, one can do this. Add ethanol and the sodium hydroxide, then you can see that the formation of the dots. You can centrifuge them, filter it, and then once you have filtered it, and after the purification of that is the dialysis procedure. That is very important. Otherwise, you get a lot of organic molecules going into the solution. So you have to remove all your organic molecules, retain only the smaller size quantum dots into these dialysis bags. So this is an important step when you synthesize the carbon dots. So you generally follow this methodology of synthesizing it and then you separating it and the purifying it. These are the steps we have followed it to get the carbon dots using the microwave. Now, when you look at the properties, we look at the size, the physical characterization, and the photophysical characterization. Now, look at the TEM analysis, where we can get something like around 4 to 5 nanometer, the average size around the 8 nanometer, one can get it. And you can also analyze the material by X-ray. And also you can look at the XPS analysis. One can look at what are the composition of all this material. So we go for the Raman analysis, confocal Raman, to find out what is the ratio between the diamond-like carbon and the graphitic-like carbon. So in this material, the ratio to Ig to Ig is around 1.91, and also look at the vibrational spectroscopy, whether what kind of functional group that are present on the surface, and that is how we analyze the IR also. Now, your surface charges can be analyzed by looking at the DLS, dynamic light scattering, and measuring the zeta potential. So, zeta potential gives you a measure of what is the extent of charges that are present on the material. Again, XPS analysis gives you the composition of this material. So, one can find out the carbon, oxygen, nitrogen, they're all present as the element. And that is how we take up this material, do a physical analysis, spectroscopic and physical analysis. And then we go for the photophysical studies on this material. When you look at the absorption spectrum, you have upcoming or steeply rising absorption spectrum. One can see it. You can find out this is the surface absorption, and the little closer to the UV region is the core absorption of the nanoparticle. Now, the interesting part of this nanomaterial is the emission is a wavelength dependent. As you keep changing the excitation wavelength, you can see the emission spectrum is changing. And because of the multiple component distribution, it is not a homogeneous component. You have heterogeneous different sizes and functionalization. Now you can see the excitation wavelength dependent fluorescence coming out of the carbon quantum dots. So quantum efficiency also we measure it. So it's around 13% quantum efficiency. Now, one can extensively use the 2D contour analysis to find out the composition or the analysis of how many components are present in this. And then fluorescence lifetime analysis, one can measure the fluorescence lifetime at different wavelengths and find out what is a single exponential. You always see that they're all multi-exponential because of the presence of multiple components in solution. So this is how you can look at the photophysical properties of all this material. Now one can also do a detailed analysis of fluorescence lifetime, and you can see that there are triple component, there are triple exponential analysis. One can look at it, it gives you a better fitting. So you always see that the multi-exponential fluorescence decay of all these quantum dots. So we have compared the quantum efficiency. Here the benchmark of the photophysical characteristics, one always looks for highest quantum efficiency carbon dot. That's the target that we always look at it. Now we could really see that the literature known materials from the natural resources, we compared it, and algal blooms found to be around 13%, almost in the upper edge. It is not the highest, still in the upper edge of the quantum efficiency that one finds it. And you also look at when you want to apply use this material for the bioimaging, and you can look at the storage stability and wide range of application of the pH of this material, photo stability. These are all important. It's fairly stable, and also influence of the ionic strength on the fluorescence intensity. Then you look at it. So there is a possibility of fluorescence quenching if you have the higher ionic strength and so on, if you have a different kind of material. So these are the parameters we analyze it to find out whether it can be used for the application that we have interest towards the bioimaging. Now we look at the cell viability also. When you want to look at the cellular image, so you have to look at it should not be toxic. So viability also, we look at its cell viability for a different duration of the hours of time, and that really tells us whether it can be used for the bioimaging application. So we have used the MCF7 cells treated with CDs, showed no significant change in the shape also. And CDs could penetrate the cells and maintain their fluorescent properties. That is very important. Then only you can use it for a bioimaging. These are the images are basically confocal fluorescence imaging, and that you can really see that there are the materials are taken up by the cellular system, and it can be used to image the cellular system that we are used to. Now, to look at what we have found for this material, it's a very nicely, absolutely green method, and from the algal bloom, which can really be used as a fluorescent marker for the cellular system. And in fact, best of our finding, this is the first report where a microwave thermolysis approach has been imposed on the plant biomass, and the obtained CDs possess strong luminescence, excellent water solubility. The interesting aspect when you work on the sensors and imaging, the solubility in water is also very important requirement that we could see with this carbon dot. And we have the admirable stability, good tolerance for the pH, ionic strength, and also the photo bleaching. It doesn't bleach when you expose light to this material. And toxicity is a low cytotoxicity, excellent cell permeability as compared to the CDs, really shown here. And I'm sure this material can be used for the many of the cellular systems, though we are not extended for many cell lines. So we have taken for the cell line that is available in our institution. We have taken it and demonstrated this material can be used for the cellular imaging. So the algae to cellular imaging, that's how we have published this in this ACA Sustainable Chemistry and Engineering. Now the other part is taking a natural, most of them we are really concentrated on the natural resources and the waste materials. It looks, science looks very simple, take these material, cook in the microwave and have some new quantum dots. So, but still, interesting materials are coming. That's the reason why we have focused ourselves on designing and synthesizing this material. Now, this jackfruit seeds, we have taken it and again used the methods to synthesize in aqueous medium, and we could really see that these fluorescence materials are coming up. These CDs can be used for again imaging as well as the sensing material. Now it is basically environmentally benign and renewable natural sources, and this is a very important aspect. And in this jackfruit seeds were used, and microwave method was used to synthesize this material. And the CD that we obtained was a eco-friendly material and potential tool to sensitize or sense the gold ion itself, and sensing a gold ion was working with this material. Now, how do we synthesize is using a microwave with the power of 600 watt and few shorter time than what we used it for algae, is almost like a 1 to 2 minutes. You can see this. And then once you have the material, dialyze it and purify it and use the material. Now we go for the again characterization of this material, gem analysis. Here we get a size or average size around 5 nanometer. Now we can also analyze the graphitic to diamond ratios. Again, is 1.98 in this case also. And Raman lines really facilitates us to identify these. XRD analysis gives you the morphology of the material that we get it. And then functionalization of this carbon dot and what we get it. And this is the functionalization that we compare it with the raw material itself. We have the jackfruit seeds, which is the raw material, and also the quantum dots we have it. We have made a comparison how exactly you have the functionalization on this material. The composition, again, carbon, oxygen, nitrogen analysis. We use the XPS to make a thorough analysis of all this material, and that helps us to find out the composition of this material. Now, when we go on to the photophysical, it looks like a similar to what we have done on the algae material, but studies look similar. Only thing is material is different, and you have a different size, different properties. You get it. Now, again, you can see the similar fluorescent behavior like excitation, wavelength dependent fluorescence. I've shown you here the normalized fluorescence intensity, so that which can clearly show how exactly the wavelength emission maximum changes as you change the excitation wavelength. And that is the interesting behavior one can see with the carbon dots. Then go for a lifetime analysis, what kind of components you have it, more than one component. So you could see that the multi-components are there. Here the quantum efficiency we found was higher than the algae, almost like a 18% quantum efficiency. You could see that the charge, negative charge also on the surface potential is larger than what we saw in the algae material. This is how, as you change the source of the raw material, surface functionalization and the dopings are different. Now we also measure the quantum efficiency by relative standard method, so that gives you the better way of measuring the quantum efficiency. We validate this material, look at the stability of the material by looking at the photo stability and usage and the pot life and so on. So this is how we could see that there's a lifetime, it can be used for a long period of time. Now you can also see that these materials are sensing the metal ion. So we can really see that it is able to sense in the sense it's the fluorescence quenching of the intensity of carbon dot as you add the gold solution to this. This is how you could see the fluorescence intensity is quenching, but the fluorescence lifetime remains the same. So it clearly tells us it is not a dynamic quenching, it's a static quenching. One can evaluate what is the concentration region, LOD, limit of detection. It's almost like one can detect the gold of the order of 240 nanomolar level. So one can identify or estimate the concentration of the gold using these carbon dots. And that was an interesting, the sensing range was better also. Again, the surface characterization using a TEM image. And we could see that as you add gold to this, there is an aggregation of the CDs happening it. And that also we could picturize better in the TEM images. So different kind of shapes of aggregation we found that is happening for the carbon dot. Now, when you look at the cytotoxicity, it is less toxic. We are used your A549 cell line, and we can really use it. And imaging application can also be, this material can be used. Now, to summarize on this material, so we have really taken the natural green material. So from this we converted into a carbon dots, and then that really gives you a morphology size of the order of 5 nanometer. It is excellent stability, very high quantum yield, a very good water solubility, functionalized highly on the surface. That is the reason why it could sense the gold ions, and which really finds a lot of application towards biology. This is very interesting aspect, and also it works like a fluorescence sensor or luminescence sensor for the gold 3+ ions. So it is interesting. You can also use it for a multicolor live cell imaging. This is another extension of this material. So this is how we can make use of these materials and image in the biological system for bioimaging, as well as the sensing of metal ion like a gold. So they're also selective. They are not really doing all the metal ion. The selectivity is also brought in. That is how we could really publish this work in New Journal of Chemistry. So the third part is the functionalized nitrogen doped highly fluorescent carbon dots, and we have really synthesized these carbon dots from the polystyrene waste. These are all waste material. You see it, and how do we really make use of them, and then which is harmful to the environment. So we thought we can convert into a useful form of the material, and that we have really made a conversion into carbon quantum dot by using your thermal methods. So you have the styrene conversion, and then which enables us to have the recycling of all these styrene materials, and which becomes a very good green methodology to convert into useful material. That is very interesting part. And highly luminescent carbon dots, it's a chlorine is also present in this material. We could really see that. And they are really, you can see that the series are also stable in various environment and exhibit excellent cell viability. We have demonstrated this is a very good material for sensing of metal ion like a gold also. And the LOD is also quite lower. Response time is also much better. This is how we could see that the styrene based series are also working for the sensing as well as for the imaging application. Again, the synthesize involves solvent thermal methodology of synthesis. We have used the doping of ethyl amines, so that really helps us to have the nitrogen doping. And once you have the fluorescence coming in this material, we really separate it and then do a dialysis, purify it, and use it for the application. Now, optimization of synthesis also, we have taken different percentages of EDA as well as the time duration of the thermolysis. Now, TEM analysis shows the size distribution. Again, the size distribution around. So now look at the synthesis optimization. Probably one can do a time optimization and the composition optimization. So we have looked at the percentage of the EDA that we use it, and then the duration of the synthesis. So once you optimize it, you go for the analysis, and the TEM analysis also gives me an opportunity to look at the size somewhere around 4 to 5 nanometers of the size of carbon dot that you get it. Now XPS analysis, Raman, and then they give you, XPS gives an idea about what is the composition, XRD gives me a morphology, and then your Raman gives me the support to identify the graphite to the diamond-like ratio. Here the diamond-like carbon is more here, it's 2.12. In the previous case, less than 2. Now it is slightly higher than the 2 number. So functionalization also we check up with the infrared spectroscopy. Right, XPS gives a support to find out what kind of a composition we have it. We have the carbon, oxygen, nitrogen, chlorine. This is how we can identify the presence of chlorine also in this. And now, how do we really make use of this material when you have the chlorine is present? Is there any property change that one finds it, all that we have explored it? Again, when you look at the absorption, emission spectrum, it is again a excitation wavelength dependent, so it keeps varying as you are looking at the different excitation, different emission maxima, one can get it. Now we also done the contour analysis to find out multi-components that are present in this material, and the fluorescence lifetime analysis. So you can see that triple exponential lifetime, one gets it the order of like a 0.8 nanoseconds, 2.6 nanoseconds. So it's a multi-exponential we could get from this material. Mostly carbon dots are it's heterogeneous and the excitation wavelength dependent, and then you also see that they are showing a multi-exponential. So now you can really see that the quantum efficiency is also higher in this case. Quantum efficiency is almost like a 20% we get for these quantum dots. And stability also we looked at it. Storage stability, photostability, ion exchange influence, and pH influence. So here the material usage range of the pH is little lower when compared to the other materials. Stability in terms of photostability, they are also fairly good, and storage stability also there is no problem. Influence on the ionic strength also is good. So you can really see that these can be used for the biological application. You also check the cytotoxicity. Now we have really seen the more than 90% cell viability of the dose of around 500 milligram per ml. So this is how we look at the cell viability of two different set of cell lines. You checked it, they are working well, we don't see a problem. And then when you go for the extension of the sensing the metal ion, gold as a metal ion, we could see that again a fluorescence quenching is happening in this, and we could selectively sense the gold ion in the presence of other metal ion also. This is how you have really selectivity is brought in extensively in this. Now, limit of detection is still lower than what we got it earlier material. So you have a limited detection is almost like a 50 nanomolar level one can detect the golds in this solution. So this is how we can really see that the different sources, different functionalization, different doping, and vary the property of the carbon dots, and that helps us to use it for a different application. And maybe the sensing mechanism also we are trying to look at it. Your lifetime remains the same, lifetime quenching is not happening, only the fluorescence intensity quenching that really tells us is again a static behavior of the quenching of the luminescence by the gold. And DLS gives us information about the sizes, the negative charge, zeta potential gives information about the charge on the surfaces that we see it. Now TEM images, as you add the gold solution to the CDs, again you can see the assemblies are happening, assembling or aggregation of the carbon dots are happening. Now when you compare the sensing property of this material with the literature known material, so the limit of detection we always compare what is the smallest concentration it can detect, and also the quantum efficient. These are the parameters we use it as a benchmark to look at this behavior of this material. So we are really compared this. Now as we said, the many our literature reported is still something around 50 nanomolar is better. These are 53 nanomolar. This work when you compare to the other reports, they're all in a larger LODs. So we could really see the enhanced LOD limit of the detection of the gold ion from this material. Now, to summarize on this material, it is again a highly luminescent, and also chlorine, nitrogen, co-dope. Cell viability is good, and you can use it for a biological imaging. And you can also see that they are selectively sensing the chlorine, the gold ion, and the mechanism is mostly on the kind of an aggregation cost quenching, and LOD is very low for this material. And we could publish it in the ACS Sustainable Chemistry Engineering. The next part is the synthesis of your CD from your organic molecule. The material that we have taken is the itaconic acid. So this is showing a different sensing behavior. This really because of the different surface functionalization we could have in this material. So Fe3 plus ion is sensed by this material, and that really finds application towards a different metal ion when compared to the other set of three materials that we used it from the natural resources and the polluting materials. Now highly luminescent CDs we obtained from this, and we have really CDs nicely characterized also. Stability of the fluorescence of these NCDs were investigated. We also demonstrated that this material can work as a good sensor for the Fe3 plus ion. Now again, as a usual method, we have really used the standardization or optimization of the synthetic parameters, wattage of the microwave, and the time duration. We found that the microwave power of somewhere around 600, and the 2 minutes or 3 minutes is ideal to synthesize this material. And again, same methodology, itaconic acid microwave, get the product and then centrifuge it, and then do a dialysis and then use it for the characterization and the application towards the series. Now, we also given a model how exactly one can really form this series from this material. Now, when you look at the TEM analysis, we get a size around 5 nanometers and something like around 3 to 5 nanometer. You can see the average size coming up. A Raman analysis gives me an information about the ratio. Again, it is 1.8. And then the IR analysis gives information on the functionalization of all this material. Now, XPS gives me an information on the composition, carbon, nitrogen, oxygen, and that helps us to identify the composition of the material. So when we go for the optical properties, so we could look at the absorption spectrum, fluorescence spectrum, and the quantum efficiency. And as usual, this also depends on the excitation wavelength. We have really normalized it and shown the picture here, how exactly the emission intensity is varying as you are, or this emission maximum is varying as you are varying the excitation wavelength. Quantum efficiency is quite high, at 32% quantum efficiency we got from this material. So our target of getting the higher quantum yield is also achieved here. And we also looked at the excitation, look at the different components that are present in the solution. So we could find that the core and then the C band and S bands were really visible. And we could really make use of the 2D contour to find out the multiple components that are present. And that gives you 2 components that are present in this solution. And lifetime average is around 5 nanosecond, though it also shows the multiple exponential. Now again, stability of these carbon dots in terms of the storage stability, pH application, and then your intensity, and also looking at the ionic strength stability and so on. So we could really see that it is working fairly well for the different regions of the pH and ionic strength. Now, when you look at the Fe3 plus, it was sensing for the Fe3 plus ion. Again, as you increase the concentration of the Fe3 plus, the fluorescence intensity also decreases. So it is again a quenching mechanism of sensing of metal ion. We could find out the LODs of around 96 nanomolar that we could have it for this material. So selectivity among all the metal ions, it shows for the Fe3 plus, whereas it doesn't sense much for the gold also, as you see for the other materials. So that's the way you can really see the selectivity here. The reason for the selectivity introduction is again the surface functionalization. We'll slowly look at this, and made a thorough analysis of the fluorescence, lifetime quenching, Stern-Volmer analysis, and also what kind of ratios of the binding of the stoichiometry of the metal ion to the fluorophore, the series that you have taken it. You have done the Benzyl-Legrand analysis. It shows the stoichiometric ratio of 1:1. Now, basically, we see that you have the complexation behavior on the surface functional groups like the carboxylate groups that we have it. That's the reason why the selective sensing of the Fe3 plus is possible with this material. Now, to summarize on this material, so it is a luminescent series were synthesized from the itagon. It is a simple molecule, and using ethylene diamine as a precursor, which also has source of the nitrogen doping. Now, series show a lot of strong luminescence, highest luminescence quantum efficiency, and also it has shown the sensitivity towards the Fe3 plus ion. So it is the mechanism of the sensing again is static in nature, and there is no dynamic quenching. The lower LOD is also important for the sensing action that is doing it. Right, this we could publish in NJC. Now the last part that we have done is we were trying to find out, is there a way one can rule out a dialysis free approach. In fact, the glycine we have used it. Glycine is not a new material for the carbon dot synthesis. We have used the material and then trying to demonstrate, is there a modification in the method which can help us to have the dialysis free approach of synthesis. That we have done it, and that really helped us to have the material. And this material shows a kind of a bichromophoric behavior, which can do redox reactions on the excited state. That is the reason why we have shown interest on this material to look at it. Now, this bichromophoric or bifunctional material has application towards the energy material, and that can really work like a dye-sensitized solar applications or mixed dye application and so on. And now we could really see that it can nicely anchor on the surface of TiO2, which can be used to have the DSSC application. So this is how we have looked at this material. Now, how do we synthesize this material? Is looking at the taking the glycine as a material, raw source material, and then you autoclave it in a Teflon lined autoclave in a muffle furnace, and then do a synthesis for a period of time, and that is and then you synthesize the material, filter it, and purify it. And now we have really avoided the one-step purification, which is the dialysis-free method. That is the important aspect, and it is simple methodology of removing the passivating agents, and no need to dialysis also. That is how we modified the method and then used it to have the a simplified synthesis of carbon dots. Otherwise, it is little laborious. Dialysis take over a long period, and then you have to really avoid this. You can avoid this by if you follow this method. Now it's a hydrothermal synthesis, and then you centrifuge it and use it as it is, so you don't have to do a dialysis. So this is an interesting aspect. Now you can really see the quantum efficiency of this material is different and a little higher. Now you can see that what is the enhanced after dialysis. If you see it, we have also done the dialysis as a reference and then try to see the what kind of quantum efficiency. We can go for a ethanol treatment that itself is giving you the uh, better material also. You have the quantum efficiency of 42%, and when compared to this dialysis basically removes the unwanted organic material. We always make it as a reference to compare it and use this as a material for the application. Now we have done the temp analysis, which gives you a size of the order of around 3 nanometer size. And again, XRD gives you the morphology, and then you get an information about the ID by IG ratio, and it is slightly lower here. Diamond to graphite ratio is 1.3 here. IR analysis gives me an information about the functional groups that are present on the surface of the CDs that we have synthesized it. And XPS gives information on the composition. Again, carbon is present, oxygen is present, and nitrogen is present. And once you have the composition analysis, we also look at the surface analysis, zeta potential analysis. Surface charges help us to find out what kind of a charges you have it. And photophysical behavior, when you go for the fluorescence or luminescence, what we call it. So you have the excitation wavelength dependency, and also you have the different types of the absorption features. One can see it when you compare it to the glycine, how exactly when you convert it into CD, absorption behavior changes. This is how one can see that the synthesis of CD from the glycine, and the quantum efficiency is the highest. One can see the 43% quantum efficiency of the carbon dot that we got from this material. And again, we follow the quantum field calculations by relative methods, and also analyze the fluorescence decay lifetimes and at different wavelengths, and the application towards the biology stability, influence of ionic strength, photostability, pH stability. So all that seems to be good. We don't see much problem. And also we check the cell viability. It's a good candidate for bioimaging application also. Now we have also taken the human lung cancer cell A549, and that really works well with this material. Now additionally, we have seen that there are donor-acceptor properties of these CDs, where the nitrogen is present on this nitrogen dope CDs we call it. So it works with the you can see the nice electron transfer reactions. You could really analyze the Sternholmer behavior, and you have the dynamic quenching behavior. And this is because of the reaction of the excited state of the CD with the methyl valigen. We have tested it, so you have a nice reductive electron transfer is seen in this case. Now we also cross-checked, is there any ground state complex formation with the methyl valigen? There is no such ground state complex formation is there. with this material. So you have the fluorescence quenching, which is dynamic in nature, and that gives an information. Lifetime also, lifetime quenching basically gives an information whether it's a static or dynamic quenching. So we compare with the fluorescence lifetime quenching and the intensity quenching. So we could really see that there is a dynamic process in the excited state reaction. Now it is also showing a multi-exponential fitting as usual with the carbon dot, multiple exponential. So we compared the KQ values, more or less they are similar. We don't see much differences. So here it can also work with the dimethyl aniline. It can also work like an electron acceptor. So you have an advantage of using this material as electron donor as well as electron acceptor, which can have the multiple bichromic. Basically, it's a bichromophoric. As usual, we have done the ground state complex is present or not. There is no such ground state complexes even with the amine, and we have used it, and that gives an information about the ruling out the possibility of ground state complex formation. So you have the excited state reaction. It's a luminescence quenching. Uh, with a KQ value of almost closer to the diffusion control limits of 10 to the power of 9, we have it. And these are all materials, good material for the excited state electron transfer. Out of the 5 material we have looked at it, this alone shows you the excited state electron transfer behavior. And these are all because of the nature of the doping and the surface behavior, surface functionalization that we see it is altering the property of the series that we have synthesized it. Again, the fitting parameters that one can see that what kind of a lifetime quenching constant and the steady state intensity quenching constant, they're closer, and they're all in the diffusion control limits. So here to summarize on this, and we have the highly fluorescent bifunctional CDs, which are really simple hydrothermal pyrolysis and synthesizing from the glycine as a simple organic material, and we got a size of around 3 nanometers. And fluorescence of CD is unaffected by long range storage solution, is quite stable, and it can have a nice photo-induced electron transfer quenching behavior with the dimethyl aniline and the methyl violin. Otherwise, this material can function like a electron donor as well as the electron acceptor. This is how we have done these 5 different types of the material, which shows the different kind of properties. One set of properties for the sensing action, and the other set of for the excited state electron transfer. This gets published in Indian Journal. Now, to summarize what I have really made it here, and we have synthesized the CD from algae, which is finding application towards bioimaging, jackfruit CD for gold ion sensing, polystyrene also gold ion sensing, itaconic acid is Fe3 plus sensing, and glycine CDs for the photoreaction. This is what I summarize it here, 5 set of material, and which really gives you a lot of property variations and the behavior variations. So this is what I really wanted to present here, and I hope you all enjoyed it. Thank you very much for your patient listening.